welcome to the stage Jordan Wiens and Peter LaFosse.
Hello. I'd like to thank Elvis for waking everyone up. So we're going to be talking about binary analysis with intermediate languages. So a bit about us first. I am Peter LaFosse, co-founder of Vector35, and longtime reverse engineer, vulnerability researcher, and now I'm the program manager for Binary Ninja, and
I'm Jordan Wiens, one of the other co-founders of Vector35. We're not lawyers. I know we put blazers on, but we just thought we'd mix it up a little bit. Believe it or not, we're actually hackers pretending to be developers and run a company making reverse engineering tools.
Yeah. So how about all of you? Everyone wake up, put your hands in the air.
Everybody.
Everybody.
There you go.
All right. And keep them up if you have ever done any binary reverse engineering. I know there's a big group over here that should be doing a lot of it.
Yeah, I see it.
Have you used a decompiler? Have you ever written any code to automate reverse engineering? Less hands. Have you ever done it on an intermediate language? Okay, less hands. And have you used an IL for any kind of other compilation tasks? LLVM, pass, or anything like that? And have you written a paper that published some research leveraging ILs? I don't see any, but if you are, come meet us afterwards. We'd like to talk. All right, so what our talk about is we're going to first kind of talk about what binary analysis actually is. Then we're going to go into why you would actually want to use it. And then Jordan's going to go over what the existing kind of state of the art is, and we're going to do some demos. So what actually is binary analysis? Well, first, remember how compilers work. We start with some source code. We are going to run it through some kind of parser to produce an abstract syntax tree that's going to be then converted into some kind of intermediate representation. And then we do our passes on this intermediate representation to produce an optimized form of the code, and then it's going to be emitted to a machine code, whatever the target is. So decompilation is kind of the opposite of this. It's the process of lifting the analysis or the native architecture to a representation that's easier to reason over. So the purposes of our talk, everything we've talked about so far could be static or dynamic, but for our talk, we're going to really focus on just static binary analysis. So one thing everyone should be aware of is that binary analysis is not source analysis. These are, a lot of people try to combine these two and say that they're kind of the same thing, and you can't really do that. There is a lot of intricacies involved in binary analysis that you don't have to do with source analysis, and vice versa. In fact, the problem here is that compilers, they mess everything up for us. Necessarily so, but one of the things that they have to do is you have in your source code potentially infinite number of variables that you have to map to a finite set of registers. What happens when you run out of registers? Well, this thing called the register allocator has to determine where each of these variables go, and if it runs out of registers, then it has to put the variable somewhere. It puts them on the stack. And similarly, with function calling conventions, you typically have a number of registers that are used, and then it starts writing these parameters on the stack. So now you have local variables written to the stack, you have parameters written to the stack, and your binary analysis is going to have to disambiguate between these two. And variable and function names and types, well, they're no more. We don't have these when we're doing binary analysis typically. We have to indirectly infer any of these things if at all possible. So the things that the compiler does then leads us to this set of undecidable problems. And an undecidable problem is a problem that requires a yes or no answer, but it's essentially it's infeasible to answer that yes or no question. And this is usually due to some lack of a piece of context that doesn't actually exist in the code that you're analyzing. So things that you might think are very simple, like identifying where all of the functions are, disambiguating code from data, determining where strings are, what pieces of data are actually pointers. These are all things that are undecidable. And then these undecidable problems lead to a set of unique failure conditions for binary analysis. And so you need to be able to handle these unique failure conditions. You need to be prepared to handle them. So what happens when stack resolution fails, when you can't figure out where all of the variables are? What happens when you think there are too many parameters to a function, or your switch resolution fails? You are unable to determine the outgoing indirect edges from a indirect jump instruction. Or what happens when you've misidentified a function that you may have a false positive or false negative when misidentifying those. So we don't say this to scare you away. It's a really interesting field that a lot of research is going into, and it's necessary to understand all of the issues that you might run into before you try to choose a solution or try to do some binary analysis on your own. So why would we want to talk about ILs? First, before we get into this, the great Twitter war of 2018 was fought over these terms. For our purposes, intermediate language is the same as intermediate representation, and we won't belabor that point. As well as these other things, bitcode, virtual machine opcode, pcode, they're all synonymous for our purposes. So here's kind of the fundamental premise here, is that reverse engineering is fundamental to understanding how binary code works. And intermediate languages are also fundamental to modern compiler design. Therefore, if you're going to be doing binary analysis, these intermediate languages should be fundamental to how your analysis is going to work. So these intermediate languages, they're generally a smaller set of instructions, more RISC-like than most of the instruction sets out there. You can see thousands of instructions for x86 and hundreds for ARM. Even something that is considered very RISC, like MIPS, still has more instructions than most of the intermediate languages out there. The intermediate languages are in yellow, and the lighter yellow is the native instruction sets. So the other thing intermediate languages get you is an architecture agnostic layer. So if you're writing a code to detect a malware on an x86 platform and they recompile it for ARM, you should be able to have a detection mechanism that works even though it's been compiled for a different architecture. So this is kind of an example of why we would want to use these intermediate languages. When we first released Binary Ninja, we had a friend that was like, okay, I'm going to write a simple script using your API. We're going to iterate, we're going to go through and find all of the system call instructions and figure out what the system call parameter is so we can then know what APIs that this is calling. So he looked at the string representation, tried to find the SVC instruction, and then stepped back and figured in his particular binary, the previous instruction always set the X8 register, this is ARMv8, and would set X8 to the system call number that he was interested in. So he wrote it really quickly, and it did what he wanted. But if we look over at the right-hand side, if you use we had to show him the way you actually would want to do it if you're using an intermediate language. And this is, you step through the IL instructions, and you ask if it's a system call, and then you just read the value of the 0th parameter. So quite a bit easier, and now it works across all the platforms forever, right? So if we were going to do binary analysis, why not just use a decompiler? And then we can run all of our static source scanning tools on it. Well, source scanning tools take a lot of, have a lot of assumptions built into them. Many of those surround the types that are available. Decompilers try to recover types the best they can, but compound types like structures and arrays are actually quite difficult, and there's lots of ongoing research to actually discover how to recover these things in an efficient manner. And these source code scanning tools rely on the fact that everything isn't just a bunch of pointer math, which is generally what you get out of a decompiler. Additionally, as you take steps towards decompilation, you have different abstractions at every layer, and each one of those layers has the potential to actually lose information and increase errors. So you might not want to use a fully decompiled binary. You might want to use some intermediate representation. So, and why wouldn't we just use C, decompile straight to C? Well, a lot of people tend to think that, okay, C is the ultimate goal, of decompilation. And we feel like this is not a great end goal, because there's a lot of constructs in C that are not generally representable, like a stack layout, right? That is something that's represented in the binary, but by the time you get to C, everything's just variables, and you don't really know what order those variables are going to end up on the stack. You have other issues like variable aliasing, like 2 pointers are coming into a function. You don't know whether or not in C that these are aliased or not. There's no C syntax for saying this pointer can or may not point to another, but in an intermediate representation, you can have that information available to you. And semantic bindings between variables is kind of a similar concept. If you have a pointer and a length, they're kind of semantically bound together, and C doesn't have this representation. And that's the whole point behind the SAL that Microsoft has, which is kind of a cool way to annotate parameters so you know how these components are bound together. So with that, I'm going to turn it over to Jordan to go over the
Keep going. Okay, great. So hopefully you see some value in using an intermediate language for reverse engineering. If not, we still have a few more chances to convert you. But in the meantime, I'm just going to talk about some of the design decisions. Oh, not the demo yet. I'm going to talk about some of the design decisions that kind of go into using an intermediate language, the choices of the intermediate languages that you can use, and it's a fairly large list. But there's a lot of trade-offs, and one thing I want to emphasize is that we're not here to say like any particular intermediate language is bad. I mean, there are a couple probably that are bad, but for the most part, there's just sort of different design choices, right? So different ILs are going to be useful for different purposes. And so this is a nice kind of summary of one particular kind of axis that influences a bunch of things. So if you have a very verbose amount of IL instructions, that's going to come from a very simplified instruction set. If I have a very small number of kind of opcodes in my IL/IR, I'm going to necessarily have a lot of them to represent some of these native instructions. Conversely, if I have a very explicit instruction set, I have lots of complicated instructions, they're going to produce much smaller intermediate results, but now my analysis code that I want to write to find a particular pattern or whatever I'm doing with it, I have to account for all of these different opcodes. There's also some implications in terms of how difficult something is to lift versus how difficult it is to parse. There's a bunch of other ones as well. For example, does your intermediate language deal with type information, or is it going to remain untyped? How are flags dealt with? You'll find that in a lot of intermediate languages, the way that they handle flags will determine how sort of readable they are, because if you explicitly enumerate every flag for every operation, it gets very large. It makes it hard to kind of visually use and to, as a human read. But maybe it makes some of your analysis easier if you just want to be able to, at any given point, query the state of a flag. Although, really, you could probably just do it just at the conditionals, right? So I think it's one kind of way you could choose to handle it. But different ILs are going to choose different decisions here. Another good point is that the more sort of like generic your framework is for your IL, you're going to choose how adaptable you are to different weird native machine code instructions, right? So if you have a very odd architecture that makes strange, like delay slots, and delay slots actually aren't that bad, but there's a number of other design decisions that can make it much more difficult for you to lift. And if you handle that in a specific architecture lifter to some sort of generic representation, then maybe it's not going to be that hard. But if you want to have a more generic, if you want to have your intermediate representation account for all possible architectures, that requires really kind of looking at what are all the screwy things that they can do. Okay, so here's an example. You're not meant to read that. That's perfectly fine. I don't know that anybody will. That's okay. But on the right, we actually have real. We'll talk a little bit more about that later. This is just test EAX from 32-bit x86. Right? That's a lot of IL that's being produced because real is a very, very small instruction set. It's being very explicit with flags, and it produces much more complicated IL than you would think about. Conversely, if you have an IL that can handle floating point instructions, for example, you might have something very concise. This is a floating point load of integer 1, which if we were doing this I don't even know if anyone's actually done this in real. My guess is not, because trying to implement the IEEE floating point in a very simplified instruction set would just be pages and pages and pages of IL, whereas it's literally a single line in a more concise representation because there actually are just floating point operations in that particular IL. Okay, so there's a lot of ILs. Again, you're not expected to kind of go through this list. You can see the slides afterwards. We'll put them online, and you can click all the references and links and look at them a little bit more closely. We'll talk about a couple of these, but these are just the ILs that are used for binary reverse engineering or security purposes, right? So these are ILs that are specifically designed to go from machine code up to an intermediate representation for you to do reverse engineering or security analysis on top of a binary. It's a pretty long list, and many of you astute readers who, or viewers, readers, might be familiar with like LLVMIR or Mixema, some of the other projects that use that. Those aren't even on this slide. That's actually a separate slide. So these are just the implementations that are going to use LLVMIR to do their analysis, and there's a whole long list of those, right? So there's a large number of these. Let's talk about specifically 6 of them. We'll go over kind of a little bit of like a quick summary of them. We'll show some examples. We've got LLVM, as I just mentioned, going to LLVM-IR. There's actually several projects that will do that translation, but we'll talk about the advantages and disadvantages of that IR. Ghidra's P-code. We'll talk about ESIL from Rodere. We'll talk about microcode and IDA, Zynamex' Real, and Binary Ninja's B and IL. So LLVM-IR. We want to discourage you from using LLVM-IR in the general case. There's a couple of reasons that this seems appealing, and it might be a good idea, but we would sort of caution you about doing this. The biggest explanation why is because LLVM-IR was built to emit machine code, right? It was built as a part of a compiler toolchain to go forward engineering, not reverse engineering. And so that there's several issues with trying to go straight from machine code all the way back to an LLVM-IR. But it is tempting, right? So one of the reasons you might want to do this is because you get a whole bunch of analysis passes. There's a lot of very useful analyses that you can get by just running these LLVM-IR analysis passes on top of LLVM. And so if you can get something that's a binary that you don't have source code to, and you can lift it back up into LLVM-IR, it seems like it might be appealing. But the problem with that is that there's, again, it's not meant to do that. And so what you can sort of see this as a byproduct of the number of those. If you go through the projects that I listed on the spreadsheet, or on the previous table, and you look at how many architectures they support, most of them don't support very many architectures, if not just 1 or maybe 2 or 3. And part of that reason is because there's sort of no cost savings in your analysis, right? You can't just do a kind of a small bit of translation and then it goes to the higher level of representation, which handles the analysis. Things like tracking stack variables, doing data flow analysis are sort of necessary to recover some of this type information, and you don't get that anywhere kind of in between LLVM. You have to sort of do it all per architecture, right? And so it's just a lot of work to go for each architecture back up to that. And again, it wasn't designed to go that direction. So it's certainly doable. There are many great tools. There is one other advantage to it I want to mention, which is it's good to re-emit. So a lot of the projects that use LLVM-IR are doing it because they want to be able to lift from one architecture and re-emit to another. So it's a kind of neat trick where if you want to take something that was compiled for x86 and run it on ARM, you can do that without source and without a full emulator, because you're actually sort of lifting it up to this intermediate representation and then using all the Clang infrastructure to recompile it back down to another architecture. And so that's actually one nice advantage that none of the other IRs, I think, on the initial table, are built for and can do well, if at all. So that is one good advantage of that. All right, so most people who have done reverse engineering are probably familiar with IDA, although their microcode is still relatively new, so people may not be as familiar with how that works. But it's been in the product since they've had hex-raised decompiler. It just wasn't exposed until, I think, last year is when they first published APIs and started kind of opening up on exactly how it works. We like to think that Binary Ninja's IL was a little bit of that motivation, but I don't know if that's true or not. So Ilfak gave a talk at Recon last year with this slides kind of the content on the left comes out of. You can see in this little snippet of assembly, we've got a very verbose amount of microcode that's kind of emitted. It's not designed for reading, and the very initial lifting is fairly verbose, but there's these optimization passes. And so they're taking the IL and they're transforming it through these different maturity levels, they call it internally. And there's a whole bunch of these sort of maturity levels and these analysis passes that happen where they transform the IL, and you see it gets kind of smaller and smaller until this last step, which is where the one right before it goes to the decompiler and it produces just an if statement in this particular example. They also have the C-tree API as well internally, which is another way to access the sort of intermediate representation that's not quite just text sourced, but another state that you can access. So Rodere's ESIL is a string-based IL, and so there's no really kind of API to get to it. You can just get these strings and you can sort of parse them, but they're postfix notation, so it's a little bit awkward in my mind because it's not quite for people. Like it's string-based, so you might think it's like meant for reading, but it's not because it's postfix notation, so it's harder to parse. But they have a lot of architectures that are supported, and so there's a whole bunch of different architectures that you might find ESIL support for. And if you want to kind of wire up into like R2 pipe and manipulate over it, you have to do a little bit of string parsing. But once you get it into something more reasonable, you can still do a lot of analysis kind of on top of it. It is a little more concise than many of the other ILs. Ghidra's P-code is sort of the new kid on the block. It's actually not at all, right? It's been around for many years. It's just now been made public this year. They have a sort of unique design in that they have what's called SLAY definitions. And so this is actually a kind of a pun on some research by Dr. Cristina Cifuentes that was, I think 1998 was the first series of papers that came out of her, the group in the lab she was working with, that described how decompilers could work. And they had a specification called SLED. And so Ghidra has SLAY. So you can tell they were reading the same papers there. And the SLAY definition is a CPU description language, right? So they describe the CPU, and then there's a compiler that takes this SLAY and turns it into the P code. P code is used both generically to, oh, it's not pseudocode. What's the other? Anybody from the audience want to help me out? P code stands for, I don't remember. It's killing me now. It's not pseudocode. That's what I keep saying that, but it's not. It's not actually pseudocode. It stands for partial, no. Something machine code, I forget what it is. Anyway, but so it's used both generically, as we mentioned earlier, bitcode, VM, opcode are used for these intermediate languages. P code is another generic term, but it's also the specific name of Ghidra's intermediate representation. It's actually pretty concise. You saw on the table earlier, it doesn't have a lot of opcodes and produces relatively reasonable stuff. It also has floating point support, has pretty good architecture support, and it's from the SLAY to the P code, and then their decompiler works directly on the P code. So Real from Zynamics is one that's kind of fun to make fun of, and I love Halvar and the Zynamics guys did good work on it. BinDiff and BitNavi are great tools, but as an IL, Real only has 17 instructions, so it produces just the most horrific IL that you'll ever see if you want to actually kind of debug it. But this is a good point where I wouldn't recommend it for general analysis. For example, type information, a lot of the other things that you would want from a reverse engineering intermediate language, they don't have. But for their purposes of doing binary diffing, it works fairly well. I mean, to this day, the BinDiff is still one of the main tools for binary diffing because of this intermediate representation they had. So it may not work for all cases, but it did work for that particular problem. Okay, so Binary Ninja's got BNIL, which is, we've sort of been like beating this drum of like intermediate languages are great, compilers use them, reverse engineering tools should use them, so let's put 9 in our tool. And so we're not going to talk about all of these. We would love to talk with you afterwards about the differences and how you kind of go between them, but I do want to highlight a couple and some of the differences kind of between them. So first, this is a tiered family of ILs. So you're going to initially, you've got assembly that's going to go to lifted IL, and that translation layer is kind of done by an architecture plugin. When you implement a plugin on top of it, you'll just write that layer, and then all the other ones are sort of internal transformations. So a little bit the way that IDA has their microcode maturity levels, except these are actually explicitly different ILs with different opcodes in some cases and different functions. And I think that's one of the things that like a Ghidra and a P code don't get you is that sort of like where do you want to look and do your analysis. IDA's maturity levels have that a little bit, which is nice, and Binary Ninja has that explicitly with all these different ILs. It's tree-based, and so that means you can kind of fold up instructions kind of nicely, make them concise for reading. Has a thing called deferred flags. Don't want to go into the details now. Come talk to us later. So let's look at a piece of assembly. So this is a much bigger block of assembly, you'll notice, than the snippets I was doing for the other ILs, because one of these properties of BNIL is that it's very concise. And so I went to low-level IL, which actually got, the image got bigger, the font gets bigger, because the actual lines of text get smaller, right? So this is actually more readable than assembly in a lot of ways. So it's meant to kind of get more and more concise, and so you'll see the higher level I go. We still have things like the stack, though, at low-level IL, and then we go to medium-level IL, which is like low, medium, high, right? It's obviously getting more and more abstract. At this medium level IL, the stack has gone away. Things are now just variables. But the point is that when you're doing your analysis, if you care about the stack and you want to know where things are in the stack, this may make more sense to ask at the low level IL. When you're doing data flow, you may want to use one of the SSA forms. There's these other things that you may want to care about, and you can use the IL for that purpose. And then this is kind of a first. So this is still in development, but this is our high level IL, and it's basically a decompiler. So this is actually the entire function that the other snippets were just showing, kind of like, this is like the first 3 lines of this bit of source code were what we were showing on this particular slide right here, gets turned into just this high-level IL, and that's very pseudocode, right? Like this is meant to be kind of a full decompiler. So it's still an IL. You can still walk over this tree of IL instructions, but it's going to not be source per se. It's just going to be this high-level IL. And then you can put semicolons on the end. You can make things look like C if you want to later, but that gets you that analysis. Okay. So why do we have so many? I think XKCD nails it on the head. Situation, there are 14 committing standards. That's terrible. Let's make the one standard to rule them all. Now we have 15. I think that's part of the reason why we get so many ILs. There's many good reasons why we have a lot of different ILs, and you may have to sort of choose which one when you want to build your analysis. many different requirements, right? So for example, there may be certain abstractions that do or don't exist on one IL that you would want to have support for. Maybe none of the existing ILs meet your needs in that regard. Maybe there's a language that you want to have support for. Maybe there is a particular architecture that's not implemented in an existing IL, and you find it easier to make your own IL for that architecture. But there are a lot of sort of unmaintained ILs. There's a lot of these that have not been touched in a while. They were just a single kind of one-off. There may also be licensing reasons why you don't want to use a particular IL. There's a couple of bad reasons, though, that there's a lot of ILs. Not invented here. I don't need to explain to a room of technical people what that means. Lack of awareness, though, I think is one that we're hoping to solve. One of the reasons we're trying to do talks like this is to make people more aware of the breadth of the ILs out there, give people sort of a flavor, ask some questions, get them thinking about what are the good properties that they would want to be aware of, and how can they use these ILs. And then there's another unfortunate reason, which is sort of publish or perish. A lot of the great research in this topic comes from academia. There's a lot of work in programming languages and compilers and reverse engineering coming out of universities, but there's an unfortunate tendency in academia to do something new and different, and you can't just iterate on something that's been around, and so you'll see a lot of new ILs come out because it's sort of like, well, we're going to like solve the problem. Instead of tweaking it in this existing open source one, we're just going to make a brand new one. So here are this is our BuzzFeed sort of like questions to ask your IL before committing. Just wait till you see number 10. What architectures are supported? What language? Nobody laughed. I'm sorry. Was it that bad? Really? You guys? Okay. Pity laugh. Whatever. I'll take it. What are the architectures that are supported? What languages are supported for? And again, languages that you want to use to query the IL maybe, or what are there different ILs suited towards a particular native source code language, because you're going to get different abstractions there. How complete is the lifting? I don't know of any IL that actually is fully complete to x86, because ain't nobody that crazy, right? Like there's a lot of ways you can do a lot of instructions in x86. And so if there are particular instructions you care about or architectures that you care about, you need to go and see if the ILs you want supports those, or you can always just add it. How are stack variables handled? How are functions discovered? It is actually interesting to me that, especially if you read a lot of like research papers doing analysis in this area, they'll say, okay, start with a control flow graph that we got from IDA, and then run this analysis and look at all the great analysis we can provide. And you're like, well, hold on, you just skipped one of the hardest problems. Like, as Peter mentioned earlier, finding where the code is deceptively hard. Like, literally just, is this byte an instruction or data is much harder than you might think at first glance. It's easy to get right most of the time. It's very hard to get right all the time. It's impossible to get right all of the time. And you can think about that trivially because data that comes in from the users can direct control flow, right? And so that's, at the worst case, means you cannot know. And so trying to recover that information is really important. But like, you need to make sure that if you care about the accuracy of your system, where is it getting this control flow information from? How are function parameters determined? Are types recovered? What are the APIs for manipulating it? Do you have data flow APIs? Many APIs will give you data flow queries where you can just say, like, where did this value come from? Is this the value set analysis? So can I tell it's a ranged value, like less than this and greater than this? Or does it just give me kind of static data flow, or does it give me no data flow? Many don't give you any of these APIs. Documentation, verbosity, and do you care about support? OK. Now I can take a breath, and we can show some demos. So the goal here, excellent, thank you. There's two different demos that we're going to run. We're going to show the problem, we'll look at the source code, and then we'll see it in action, and we'll cross our fingers that it works and we don't get hit by the demo gods. So I went to Stack Overflow, as one does, and grabbed a copy of some MD5 source code. I don't know, I just Googled like, MD5 implementation. And so I built this MD5 into a library, compiled it, and we can open it up in Binary Ninja, where I've got MD5 init, MD5 update, MD5 final. I've got the names of these functions here, for example, because I compiled it with symbols, but you don't often have that when the binary, do we lose? Oh, we're still there, okay, just my confidence is out. You don't often have these symbols. How many people have reverse engineered MD5 before only to realize, like after several hours, that it was MD5 or any encryption? Okay, the people that have, yeah, you're lying if you don't raise your hand. So like this has happened, and this is a terrible thing. Like when you, yeah, I'm sorry for your loss. Like this is like a painful thing when you reverse engineer something that's really just a statically compiled library, right? And so finding these crypto functions is a very useful thing. There are several plugins that will do this. IDA ships one in their default APIs. There's several other third-party ones. There's one somebody wrote on Binary Ninja called like CryptoScan. And all they do is they go through the binary and they look for particular constant values. Because if we look back at our source code here for MD5, we can see like in this init, there's literally, we're just seeding it with these constant values. There's these transforms that are going to happen. These sort of magic values, if you do a lot of like reverse engineering in these areas, you literally can just recognize them. But it sure is nice to have a plugin that will just go find them for you and tell you like, yeah, these are all MD5. Don't waste your time reversing them. So let's go ahead and run this particular plugin. We've got our binary, and we're going to do what's called a scan for crypto. And it's going to go look for all the constants, and we're going to find some results. Like, OK, so there's two separate sections. This font is a little bit small. Let's zoom in up here. We've got our data constants, and we've got our IL constants, right? And so you can see in this case, it turns out MD5 and Kasumi, which I've never heard from, apparently share or there's different constants, but they're both in this sample. So maybe this is a variant of MD5, like the Kasumi implementation of MD5. I didn't know that, so that's a lesson learned. And I can click on the address, and I can go and see where that constant kind of came from. Like you can see, yep, there's our data in our data segment here, data section that contains some of these constants. Great, we found them. OK, but what happens though if a piece of malware just like decides to obfuscate these constants at all? Like maybe they're going to, let's go over here to my modified one, and now literally all I'm doing is I'm going to XOR it with A's before I initialize that structure, right? So I've built that as a library, and now if we open up that binary, we've got our obfuscated version. Scan for crypto. We still find some stuff. Now, like, why is that, right? So if we look here, now we've just got these IL constants. So those data constants are gone. Because if we look in the data section, we're not going to find, so if we look before, we were at address 1170. So let's go to, let me see here. So these particular constants here, so actually the address is different on this one, are not the same constants, right? Because they got XORed. Like this is not hard. But the problem now is that our sort of library isn't going to be able to find them. But this plugin still worked. Like how did this plugin still solve this problem? And if we look at the source code here for CryptoScan, we can see what they're doing is they're actually pulling their constants out of the intermediate representation. They're pulling it out of, in this case, the medium level of IL, because again, they didn't care about stack, and so they just wanted the kind of higher level abstraction. And so if we go back and look, let's take just a second. It's worth commenting that this is, because Binary Ninja's IL is sort of tree-based, you're going to either need like a work queue or a visitor function. You can't just kind of like linearly scan over each instruction. You have to kind of recurse down into it, because each instruction could be a tree of expressions. And so you'll see that this is pretty straightforward here. This is a recurse retrieve consts, and it works the way you'd expect. If it's currently a constant value, it adds that to the results list. Otherwise, it recursively goes through all the operands. Right? So it will just literally take every instruction, recursively look through it for these constants, and like that's it. There's actually lots of other code in this thing to handle the library and to build the list and to generate the report. Like that's it though. That's all it takes to find these constants. And if we go back to our binary, in the initialization function, we can see that we just see this is one of those magic constants right there. It's showing up in the annotation on the side because the data flow system is like, well, I'm just reading this constant value, comes out of the data section, so I know it's read-only. It's being XORed with this other constant value. Therefore, I know that the constant value is currently this. Like that doesn't actually appear anywhere in the disassembly. If you look in a debugger, you'll see it only in the registers at that moment, but you'll never see it in the static disassembly. So that's one of the nice things you get by like having this kind of data flow analysis. The next problem that we're going to have is, let me see. FireEye did a great blog post a couple years back where they talked about dynamic function resolution. So they were talking about a particular piece of malware that was hiding its functionality. So like, you know, one of the most kind of, the two quickest ways to find out the functionality of a binary are look for all the strings and look for all the imports, right? Like what are all of the libraries that this thing calls into? Unfortunately, many pieces of code will dynamically resolve libraries. So they'll use DLSim, they'll use getProcAttr, depending on the platform, and they'll actually load these libraries, they'll get a function out of it, and then they'll call into that function, but you'll never see it in the import list. And so if you're just trying to kind of quickly scan a binary, you won't see what this functionality is. So like this is like this called a triage view. It just shows the imports on a particular binary. And this is actually one of our Binary Ninja libraries. We have our Python loader that, because it can work with different versions of Python, will actually load the library for Python on the fly. And you can have different settings for different versions of Python. But we don't see any Python APIs here because they're dynamically loaded. They're actually called in here with, let's see, this one is ELF, so this one's going to be DLSim that it's going to work on. And if I do this load dynamic imports, and it works, we got some more things down here. So now we can actually see that we've got new imports that are actually showing up. And so these are Python APIs that are being called from. We can, and most importantly, we don't just see, so like this was somewhere in the BSS, right? So it's going to be initialized to 0. If we actually go over and open this binary again and go to that same address, let me copy the address out. And just go to that address. Right, these are just, there's nothing there. Like the normal binary has just zeros, but because the DLSim is going to be loading these function pointers at that location, this load dynamic function pointers is actually going to create pointers here to these functions. And now we actually have cross-references. And so that's actually what makes it really nice, is anything that calls that, calls through that, you can see there's an indirect crawl through that pointer address. We've actually got that symbol name, and I can switch over to the IL view. It actually looks like a call, like it's got a call to that function. We can see all that kind of useful stuff. So this is a little bit like a dynamic bit of functionality. Normally, to get this kind of dynamic resolution, you would actually have to do it on a debugger, and you'd have to breakpoint there, and you have to pull it back out, make sure you got it, or you have to manually fix these up. So this is a nice way that the intermediate language kind of gives you some of that. You can even propagate type information, a little bit more of that. So the code for that one is actually primarily right here, where it's looking for calls to the addresses, and then it's going to create the type information and just apply it at that address. So again, it's going to be this recursive, like walk over the whole thing, look for the calls, and then make sure it's one of the things that we care about. And it's going to pull out the argument to the DLSim or getProcAttr. The advantage of the IL here, one of the advantages, is that this works out of the box on both PEs and ELFs, Mac, Linux, Windows. It works on all of them because at the top, all it does is to say, well, on Windows, I'm looking for getProcAddress and getProcAddress.iat entries, and on Linux, FreeBSD, and Mac, I'm looking for these other APIs, but they actually just work essentially the same. So it can resolve all these, and this is literally the only platform-specific code kind of in the whole thing, and so you get that sort of portability of platform and even architecture, right? If this was something compiled for another architecture, it would just work with no changes. All right, so we can go back to the slides. There are demos. If you have any questions, we would love to talk to you. We're going to be over to the side. Thanks for staying with us. Thanks for staying awake. Take care.